So excited to give this talk, and it's been really exciting to hear the other groups and the ins and outs and possible relationships. Um, our group has really tried to push forward on understanding behavior and extracting out not pose itself, which several excellent groups have done, but the spatial temporal patterns of pose that we might often call behavior and actions. So for a few years ago, we came out with an unsupervised algorithm that can discover these patterns of behavior. We don't tell the algorithm anything. And it actually, as sort of a ground truth, when we look at motor cortex or motoric striatum in mice, we see that many neurons, this is from a neuropixel, have a robust response for one or several of these behaviors. Everything here is aligned to the onset of the behavior. And we've more recently moved into supervised algorithms, particularly because they're really necessary for social behaviors or behaviors that are nuanced. And so earlier this year, we came out with not B-side, but A-side, which is an adaptive or an active learning mechanism that with only a fraction of a training data set, which is really the difficult part about supervised learning, is the large amount of data that a user must train on these social behaviors from the CALMS 21 challenge. We're able to outperform with just a fraction of that behavior. And compared to other leading techniques, the method outperforms. And so one of the things that the grant is designed to do is to help incorporate both the supervised and unsupervised branches of the algorithm, so that one might be able to get large categories of behavior and then do unsupervised discovery. And here, within the investigate class in that benchmarking data set, we're able to discover orogenital approach, which is subclass 2 here, and mutual exploration, subclass 5. So this is an exciting avenue that we're looking to apply as part of this grant. It also works on humans, both social and non-social behaviors. And here's from an example data set, all sorts of surprisingly nuanced behaviors. It was actually able to learn quite quickly, and it's packaged all as a user-friendly package. So this is part of the grant, but the real innovation moving forward that we're looking to achieve is first to incorporate different types of information other than pose dynamics. So get pupillometry from a head-mounted selfie cam, physiology, and vocalizations, and then to benchmark this in two different contexts that I'll get into in just a second. One feature that I've heard mentioned a couple times in different ways today that we've managed to find different ways to solve is all of this data comes in per animal at 4 terabytes a day. And because we're recording continuously 24/7, if we don't process it today, tomorrow we have 8, and the next day we have 12 terabytes to deal with. Happy to talk to anyone about our solutions or improve upon them. And so in terms of the additional signals, we're looking to integrate. Some of them have been mentioned already, including vocalizations and heart rate. And one challenge will be that these signals occur at different scales, have different sort of inherent dimensionality, and of course, different sampling rates, and how to best deal with these different data streams in order to identify different behaviors. So certainly running and running while screaming, I think we'd all agree are two very different behaviors. Thanks. And then the two benchmarking contexts. One is a single animal intruder array in which we deposit a foreign mouse's urine stack, and then look at the changes across behaviors and neurophysiology continuously over time as they respond to this intruder urine stack. One interesting thing is there's been a lot of interesting or interest in the different compounds, some of which are designed to be released at different points in time. And so we might be able to link changes in behavior or physiology with the sort of decomposition of this social cue that the animal is interacting with. And the other is resource scarcity, in which we'll take an animal and water restrict it and then return it back to ad lib water, which is both interesting in terms of the natural experiences that these mice will have, as well as the fact that almost every trained task that most neuroscientists do revolves around restricting the amount of water an animal has, and that may lead to some distinct changes in both gut microbiota, overall physiology, and neuroactivity. So lastly, our team, which is based here at Carnegie Mellon, Genelia, with our dyed-in-the-wool social ethologist, Royan, as well as our more computational side at Pitt and here at Carnegie Mellon. I'm happy to take any questions.